Okay, today we are discussing a previous problem. This is a problem which was asked for the 2018 May examination of heat and mass transfer. I'll read the question and we will discuss how to solve the problem. Water at a rate of 4 kg per second is heated from 40 degrees Celsius to 55 degrees Celsius in a shell and tube heat exchanger. On the shell side, one pass is used with water as a heating fluid and at a mass flow rate of 2 kg per second and entering the heat exchanger at 95 degrees Celsius. The overall heat transfer coefficient is 1500 watt per meter square Kelvin and the average water velocity is 0.5 meter per second in a 2 centimeter diameter tube. So because of space limitations, the tube length must not exceed 3 meters. The questions are: calculate the number of tube passes, number of tubes per pass, and the length of the tubes. These are the three questions. So keeping in mind there is design constraints specified in the problem. We will see the questions. We will try to collect the data given in the problem. This is actually a shell and tube heat exchanger. There is one shell pass and the tube passes are to be decided based on the constraint. The constraint is that the maximum length of the tube per pass is limited to 3 meter. Now we will try to solve this problem. So this is a shell and tube heat exchanger. The inlet temperature, water is to be heated from 40 to 55 degrees Celsius and water flow rate is 4 kilogram per second, and this is heated with the help of again hot water which is available at 95 degrees Celsius at a rate of 2 kilogram per second, and the hot fluid is flowing through the shell. So the shell side one pass is used with water as a heating fluid. So the overall heat transfer coefficient is given. So here specific heat of water, either the cold or hot water is not given, which can be taken from data book, or we know generally the specific heat of water will be known, which can be taken as 4187 joule per kilogram Kelvin. The variation of temperature, variation of specific heat with the temperature is not to be taken into consideration. Now we will write down the data given. So hot fluid is flowing through the shell and which is coming at an inlet temperature of 95 degrees Celsius, which has a flow rate of 2 kilogram per second, and the specific heat can be taken as 4187 joule per kilogram Kelvin. This is not given in the problem. We can take this from either data book or from the known value. Now the velocity of water inside the tubes is 0.5 meter per second and mass flow rate of water in the tubes is 4 kilogram per second. The inlet temperature of the cold fluid in the tubes is 40 degrees Celsius and the outlet temperature of the cold fluid is 55 degrees Celsius. Specific heat is common for both the hot and cold fluids. Now cold fluid is a tube fluid. The velocity is given. So first of all we need to calculate the number of tubes. So this can be calculated by the mass flow. So for that what we do is mass flow rate of the tube fluid to be calculated. For that, number of tubes into mass flow rate through one tube will give us the total mass flow rate inside the tubes. N into rho into pi by 4 d square into velocity is equal to 4 meter. In this equation, the only unknown is number of tubes. Therefore, n tubes number of tubes is equal to 4 divided by rho is 1000 kilogram per meter cube. Area is pi by 4 into 0.02 whole square because 2 centimeters is the diameter of the tubes, which is given in the problem, and velocity is 0.5 meter per second. Substituting the values, we will get number is equal to 25.5. So we cannot have a fraction as a number of tubes. So we'll go for 26 tubes. So number of tubes is 26. Now, the heat transfer based on the heat balance of hot and cold fluids, like mass flow rate into specific heat into temperature difference, Thi minus Tho of the hot fluid equal to mass flow rate into specific heat into temperature difference of the cold fluid. Here, the only unknown is the hot fluid outlet temperature. All the other terms are known. So, from this equation, the outlet temperature of the hot fluid is equal to 65 degrees Celsius. When we substitute mass flow rate into specific heat into 95 minus Tho is equal to mass flow rate of cold into specific heat into 55 minus 40. So the hot fluid outlet temperature is obtained as 65 degrees Celsius. So now we have all the four temperatures known. The LMTD can be calculated only if all the four temperatures are known. Now, the actual heat transfer is equal to mass flow rate into specific heat into Thi minus Tho. Substituting the values, we will get the heat exchange is equal to 2,51,220 watts. Or in kilowatt, we can write it as 251.22 kilowatt. Now, how to calculate the LMTD? LMTD of a shell and tube heat exchanger is equal to a correction factor into LMTD for counterflow arrangement. Now, for counterflow arrangement, the LMTD is given as Thi minus Tco minus Tho minus Tci divided by logarithm of Thi minus Tco by Tho minus Tci. Substituting the values, the LMTD for counterflow arrangement is obtained as 31.915 degrees Celsius difference. So this is to be multiplied with the correction factor. So how do we get the correction factor? Correction factor for LMTD, one shell pass and in many tube passes. One shell pass and any number of tube passes is given by this chart. So this is a schematic of it. So capital T1 and capital T2 are the temperature, inlet and outlet temperatures of the shell fluid, and small T1 and small T2 are the inlet and outlet temperatures of the tube fluid. Knowing these values, now we can calculate obtain the correction factor from charts available in the data book. So for that, these temperatures are explained here. We have to find out two factors P and R. P is given by T2 minus T1 divided by T1, capital T1 minus small t1. So this is the temperature difference of the tube fluid, and this is the maximum temperature difference, inlet temperature of the shell fluid minus inlet temperature of the tube fluid. So substituting the values, we will get the factor P equal to 0.27. Now R is capital T1 minus small t1 divided by small t2 minus small t1. Capital T1 minus capital T2 divided by small t2 minus small t1. That is the temperature difference of the shell fluid by temperature difference of the tube fluid. Substituting the values, 95 minus 65 divided by 55 minus 40, that is equal to 30 by 15, that is 2. So we have the factor P equal to 0.27 and factor R equal to 2. So now based on the values of P and R, the correction factor for one shell pass and any number of tube passes, 2, 4, 6, etc. Can be obtained from this chart. We calculated P is equal to 0.27 and R equal to, the factor R is equal to 2. So corresponding to the x-axis shows the value P and the different charge gives the value of Q. Sorry, the factor R. So from this value corresponding to 0.27, this is 0.2, this is 0.3. In between we have 0.25 and 0.27 will be somewhere here. So projecting upwards to the chart 2. So 0.27 and which interferes 2. So 0.9 slightly, sorry, this is slightly above 0.9. So this can be, they see this is 0.9, 0.95 and 1. So here it intersects this chart at a value of maybe we can take it as 0.92 approximately. So the correction factor is obtained as 0.92. Now let's go back to our PDF solved problem. So from these values, the correction factor is obtained as 0.92. Therefore, LMTD of the shell and tube heat exchanger is equal to 0.92 into 31.915, which is equal to 29.36. So we have all the values. LMTD is obtained. U is there, overall heat transfer coefficient. Now the length of the tubes or the area of the tubes can be obtained by total heat exchange is equal to number of tubes into surface area per tube into overall heat transfer coefficient to LMTD of the shell and tube heat exchanger. So in this we can see that even the diameter is known, number of tubes is found to be 26, length of one tube is equal to L, which is unknown. So this can be calculated by substituting the other values, known values. L is equal to Q divided by number of tubes into pi T into U into delta T of shell and tube. S and T stands for shell and tube. Substituting the values, we will get the number of tubes to be 3.49 meter. But the permissible length, the maximum length is 3 meter. So we cannot have a tube length of 3.49 in single pass. So what we do, we make this into 2 tube passes. So if we make this into 2 tube passes, then the length of one tube pass is equal to 3.49. Total length of tube divided by number of passes. So 3.49 divided by 2 is equal to approximately 1.75 meter will be the length of one tube pass. So these are the answers: number of tube passes and number of and length of tube per pass is 1.749, and the total number of tubes is already being found out to be 26 in a previous calculation as shown here. So we will stop.